in the textbook and most of the videos have found they've to get very technical, and it doesn't need to be that hard. So I thought I'd record this video for this section myself. And you can certainly find other things if you want, but see if this works for you. Um, a lot of this is stuff you did at pre-calc or and early in classes. So we'll apply some derivatives to it to help us graph it. This one at the end. The derivatives do help us graph it when we get a graph by hand. But let's start back at the beginning. So there's some things that can happen as x goes out to positive infinity or x goes out to negative infinity, and um, well, one thing that can happen is x, like, I don't know, we got some things going on here in the middle. We don't know what. In this case, the limit as x approaches positive infinity for f of x that would go up to infinity, right? It's heading up, and conversely, if for this one, the limit as x approaches negative infinity for the function, well, that would go to negative infinity, and I mean, a linear function does this. There's also rational functions that have oblique asymptotes, and that's what an oblique asymptote is when it is a nice horizontal line. It heads off. It doesn't have to be like this. It can have like a negative slope kind of thing going on too. And we'll look at how to find that and figure that out. Um, it can also the other things can happen is it can have a horizontal asymptote. So we've got some stuff going on in the middle, and we can even have two horizontal asymptotes. As we could say, as one's going off to the right, as the limit as x goes off to positive infinity is one value, and as it goes off to negative infinity, there's a different value, or it could be the same value. And one thing that happens with folks, they get confused a little bit with, so like if I've got this horizontal asymptote and the function flips up above it and then come back down below it, it's okay if the function crosses the line that's the horizontal asymptote, because that's anything can happen in the middle. We're really only concerned about what happens out at positive infinity, what goes out to negative infinity. And they actually say in the textbook, might be worth mentioning. So they say the limit as x approaches infinity, or it could be negative infinity, it could be plus or minus infinity for a function. If that approaches some number, some L, I think they use L because of the limit, that means there's a horizontal asymptote. And we'll talk about functions and how to figure that out later on. Um, and then there's some other things that can happen, like if you think about a sine function, uh, that doesn't really have a horizontal asymptote because the limit as x approaches positive infinity for sine x or cosine x or tangent x, most of those trig functions, that would be an oscillating, right? It just goes like this. It doesn't go above 1 or below -1 if it's not transformed. So, but there's no horizontal asymptote, and it just repeats. Is there a special name for that? I don't think so. But there isn't an asymptote, okay? Um, so there, we talked about that. We kind of talked about that. Um, we've started introducing it. Okay, let's go look at some more questions here. So for this one, this is my notes here. So what I'm really trying to do is I'm trying to find the limit as x approaches plus or minus infinity for 2 plus 1 over x. And what I'm trying to do is figure out, well, is there a horizontal asymptote here? Well, what happens? So like I said, there's all kinds of stuff you can do. Um, if you look in the textbook, they do all this math, this theoretical stuff, which it just isn't necessary. You're better off just thinking about it. Um, so what happens here? So I'm going to do 2 plus 1 over a large negative number, and I'm going to write negative infinity. So that's basically the limit as x approaches negative infinity. Now, we can't write 1 over infinity, but what I'm saying is it's 1 over a negative large number. Well, isn't 1 over negative 1,000 or 1 over negative 1,000,000? or 1 over negative a billion, isn't this number going to 0? Yes, it's a negative number, but way out at infinity, it's getting so small, it doesn't matter if it's negative, because 2 minus 0.00000000001, that's pretty darn close to 2. So in this case, because, and the same thing happens if I'm a positive infinity. I'm positive, 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 positive. That would be 2 plus a very, very small number. So basically, this has a horizontal asymptote. It has a horizontal asymptote, would be HA would be the line y equals 2. It's important to write it as a horizontal line, too. If they ask you, what is the horizontal asymptote? Just don't say 2. Say y equals 2. Okay, so that's how that works. Not too bad. So here's like 3 different kind of versions. These came out of the textbook, out of the examples, folks. And they're doing all this math with it, as I said. So, do you see how this is basically the same kind of thing, except it's even going faster. X gets huge. That's 2 divided by a huge number is basically 0. So that has a horizontal asymptote, and it's y equals 5. Okay. So, so for sine x over x, we've seen this before. Remember, how we've looked at it before is we said, what's the limit as x approaches 0 for sine x over x? And there's a lot of ways to do that. We're going to learn L'Hopital's rule after exam 1, exam 2 here, and that's even easier. That limit was 1. Um, but now that's not what we're asking here. Here we're asking for out at positive or negative infinity. Now we know. So one thing you can do is you can say, okay, so what's the limit as sine x? Here we go. We can say what's the limit as sine x approaches infinity, and what's the limit as x approaches infinity. I won't write the infinity thing. So this bounces back and forth between plus or minus 1, doesn't it? But this keeps growing. It could keep growing to the negative side. It could keep growing to the positive side. So basically what I'm going to get is I'm going to get 1 over a big number. So, or it could be 1 over a negative big number. In either case, that's approaching 0. So this has a limit of 0 out at negative infinity and positive infinity, which means the horizontal asymptote is y equals 0. Okay. So what happens up close to 0? Well, we know that's 1. So we might be able to think about what's going on with that. Well, I don't know. I don't know if I want to get too into that. This is what I wanted to do. Okay, so now for cosine x over x plus 1, remember how this one here is almost the same thing as that sine x over x. We know cosine is going to bounce back and forth between 0 and 1, negative 1 and 1, I mean, and this is going to get really large. So this goes to 0. And remember, when we take limits, you can take the limit of this plus the limit of this. Well, this says that x is always 1, right? So this goes to 0, that plus 1, that limit is 1. And so y equals 1, there's a horizontal asymptote. Okay, so we're figuring out what's going on out at infinity, whether or not it has a horizontal asymptote or a vertical asymptote. Um, we haven't talked too much for the vertical asymptote yet. Well, we know that this doesn't have x can't be 0 there, right? So there's a problem with the domain. Whether it's a whole or vertical asymptote, that's yet to be determined. Okay, then we come to the arctan function. Well, if you remember, let's do a little pre-calc here. Arctan tells me what's the angle when I know the decimal or when I know the values. Right? This is saying back when we did derivatives of inverse trig functions is where we talked about this. Um, so this function tells me, hey, if you have this answer, what's x, right? Well, it just so happens, and if you think about the tangent function, right? The tangent function has a vertical asymptote at negative pi over 2 and positive pi over 2, and then it repeats, right? And they look like this. And that happens because if it's y over x or opposite over adjacent, Down here, this is going to, let's see, this coordinate is what? 0, -1. And so if I try to say -1 over 0, that's undefined. That's what gives me the vertical asymptote here. The same thing happens up here at positive pi over 2, 0, 1. 1 over 0 is undefined. But we can find values anywhere in between, right? Right there it's 0 because it's 1, 0, right? That's why it's 0. At 0 radians, um, 0 divided by 1 is 0. That's why the tangent graph crosses there at 0 radians, okay? Now, the thing you want to remember, so how can I remember all this is when I'm start talking about the inverse functions. Well, when we talk about an inverse function, the old x becomes the old y becomes the new x. The old x becomes the new y. So if I've got vertical asymptotes, which are x's, the horizontal asymptotes in the inverse are the old x's become the new y's, right? So we know arctan looks like this. This is 1, 2, 3, -1, -2, -3, and of course all those decimals in between. And then the outputs are between -pi over 2 and positive pi over 2. So because the old tangent function has the vertical asymptotes at those values, the arctan function has horizontal asymptotes at those values. Okay, so how's the easy? I mean, is there a way to do this algebraically? Maybe I think it's easier just to remember what these arctan functions look like. You know what the tangent function looks like. That just gets rotated around that line y equals x, right? It's because it's an inverse. So that has horizontal asymptotes. It has two horizontal asymptotes. As x goes out to negative infinity, the horizontal asymptote is y equals -pi over 2. As x goes out to positive infinity, the horizontal asymptote is y equals positive pi over 2. Okay, so that's the ending behavior for that function. Now we get into rational functions, and when we're dealing with rational functions, this is probably something you looked at in pre-calc. I know if you took my pre-calculus class, you certainly saw it. Um, but so what happens is when we go out to infinity or negative infinity in that case, the ones don't really matter, right? Because two two times a big number plus one isn't that much different from two times the big number. And same thing for the denominator. 3 times a big number minus 1 isn't much different than 3 times that big number. So basically what we can do at infinity is we can ignore the plus or minus 1. And then x over x, can I cancel out the x's? I know we aren't supposed to, but in this case, remember, it's a number. I mean, if it's a million, that'll be 2 million, I need 6 zeros, right? Over 3 million. So now I'm not crossing out a number, I'm just simplifying that fraction. See how we get 2/3 that's left? So the horizontal asymptote of this rational function is the line y equals 2/3. The way that I talk about this, I know I'm not alone in this, this is the same power in top. The degree of the numerator is the same as the degree of the denominator. There's a horizontal asymptote, which is the coefficients of those leading terms, okay? So that'll always happen. It doesn't matter what the exponent is, as long as it's the same expression, the same power function, it'll be the same. Now in this case, let's see here. So I want the limit, I might as well get formal, as x approaches plus or minus 1, or plus or minus infinity, and we get that. So in this case, you see how I don't have the same power? And so let me back up a little bit. As I go way out to infinity, the 7 doesn't matter. And actually, the -5x and the +2x don't matter because the exponent rules, right? A million squared is a lot bigger than 2 times a million. Same thing with a million cubed. So we can actually ignore everything up until 3x squared over 4x cubed. And then, because this is a bottom-heavy function, actually we can do a little simplifying here. I can do this as 3 over 4x. Well, the 3 is constant. The denominator grows without bound. So that means I've got 3 over a big number. That's y equals 0 is the HA. So because this is a bottom-heavy function, the horizontal asymptote is y equals 0. Okay? So same power, coefficient ratio of the coefficients. If this was second power and this would be second power, the HA would be y equals three quarters. But because the denominator is bigger than the numerator, the degree of the denominator is bigger than the degree of the numerator. The bottom grows faster. Y equals 0 is the horizontal asymptote. Okay. Do this one first. The limit as x. The limit as limit as x approaches plus or minus infinity here. Actually, let's split that off into separately because it acts differently on either side. And then I'll just get this ready. The limit as x approaches negative infinity. So if I look at this function right here, it's a linear function over a square root function. I can still use that idea as I go out to positive infinity. Let's go out to positive infinity first. The 2 doesn't really matter. Even the 5 doesn't really matter way out there at infinity. Even though it's under the radical, right? If I'm get a square root of a big number plus 5, the 5's really not going to have a lot of effect with it. So then that leaves me 3x over the square root of 4x squared. And can't I take the square root of 4x squared? Isn't that 3x over 2x? Now, technically, though, this is a positive number, right? So we want to think about it. It's an absolute value, just so we don't get confused. Now, so far, this works the same for both of these. Actually, let me write this separately. 3x over the absolute value of 2x. Let's make sure that looks like an absolute value, not 12. Okay. So here's this function. So won't this be a positive big number over, and see how this is the same power, same degree? So a positive big number, so it's kind of like 3x over 2x. Remember, x is some positive number, and in the bottom it's definitely positive. So won't that be a horizontal asymptote of y equals 3 over 2? So that's as I go out to positive infinity. Then what about, oops, did it get locked in? Oh, it got locked in. Okay. So now as I go out to negative infinity, 3x over the absolute value of 2x. Well, in that case, I'm going to have a negative number, a negative large number, negative 3 times a large. Maybe I ought to change how I wrote that, just because it's not 3 that's negative, though it turns negative. So this is 3 over a negative big number, or 3 times a negative big number, over 2 times that same big number, but it's positive. In this case, won't it be negative 3 over 2 is what I'm trying to get you to see? Because then going out to negative infinity, that numerator becomes negative. The denominators are always positive because of the absolute value. Okay, so when you get these kind of radical kind of things going on, you can simplify it. You got to pay attention to what's positive, what's negative. I hope that's not confusing. Okay, now for this rational function, do you see how the numerator is bigger than the denominator? So the top is growing faster than the bottom. Well, when I have, so again, as I go out to infinity, the 2 doesn't matter, the 4x doesn't matter because the square grows faster. So I'm really left with 3x squared over x, and then I can cancel out an x. That leads me to line 3x. Well, what happens as x gets really big? This gets really big. What happens when I go out to negative infinity? Well, this gets really negative. So this has no horizontal asymptote. What it has an oblique asymptote or slant asymptote. Some textbooks talk about this as. Okay, and when we try to graph it, it's good to know what that oblique asymptote is. Um, so let me delete this and we'll talk about that. So to find that horizontal asymptote, what we're going to do is we're going to do a little synthetic. We won't do synthetic. We could do synthetic division, but I almost think that in this case it's easier to do long division, polynomial long division. Okay, so 3x squared plus 4x. So what we'll do with long division is because the reason we want to do this is you can write these when it's a top heavy function, you can write these down in the form the quotient plus the remainder divided by the denominator. And I'm treating these as functions because they can be functions, right? They can be constants, but a constant is a function, right? So in this case, what times x is 3x squared? Well, that's going to be 3x. So then I'm going to multiply. I'm sure you probably remember doing this, but I'm going to do it slow in case you don't. 3x and 3x squared plus 6x. So what I'm going to do is 3x squared plus 6x. Remember, then we're going to change our signs because you're dividing. And that way the 3x squareds are gone. I'm left with negative 2x and then plus 0, I guess. I mean, it's nice to, this is a little weird because there's no constant term there. So then I ask myself, here, let me do a little erasing. Then I'm going to ask myself, what times, I don't know if it's letting me erase it. Oh, it does let me just delete that. Good. What times x is negative 2x? Well, that's minus 2, minus 2x minus 4. So I'm going to get minus 2x minus 4. Change your signs. That leaves me 4 with the remainder. So plus 4 over x plus 2 is how I'm going to rewrite this. So what do I got going on here? I've got my quotient, so that's my oblique asymptote, that's my slant asymptote. And then I've got the rest of this rational function. So this is what happens out at infinity. This is what happens around, in the middle, in between all those. Okay, so we'll hold this. I won't do any more. I won't do any more yet with this because we're going to do some derivative work to help us out with that. So with a rational function that doesn't have polynomials, it's very similar. Just be careful. That's all. You can't automatically say it's going to happen. In this case, it does. I want to. Well, let's look at it. So as the limit as x goes out to negative infinity for this function, well, that becomes 2 plus 3e to the negative big number. Let's make that big number be 100. Okay? Over 7 minus 5 times e to the negative 100. Well, negative exponents mean we can kick them downstairs to the denominator, right? So that becomes 2 over 3 e to the positive 100 over 7 minus 5 over e to the 100. Well, e to the 100 is a huge number. 3 divided by that huge number basically goes to 0. Same thing there. So as with a polynomial, we could say the horizontal asymptote is 2/7. And that same thing happens with positive to positive 100. Well, I think it does. Let's see what happens here. I mean, that would become. Oh, yeah. I'm glad I'm doing this. I'm glad I'm doing it. Go out on the positive side, what happens? Well, in this case, 3e to the 100 is much bigger than 2, right? So in this case, the 2 and the 7 don't matter. And then I've got 3e to the 100 over negative 5e to the 100. Those can cancel out because they're the same. So in this case, it's the other piece that rules. So here we're seeing 3 to the negative 3, y equals negative 3/5 would be the horizontal asymptote. So depending on whether you go to positive 100 or negative 100 would be the difference. So what's this going to look like? Well, let's see. It's going to be y equals 2/7, pretty close to 0. which would be, so something, whatever's happening in the middle, we don't know, but we know this function would settle down to horizontal asymptote of y equals 2/7 out to the left and down to -3/5 out to the right. So two horizontal asymptotes depending on what you're doing. Okay? And this actually comes as another application. Here, just a minute. What if I don't have, like, what instead of a constant, what if I get a function? And it's no longer a rational function, right? So what's the ending behavior? What's the horizontal asymptotes here? Or are there horizontal asymptotes? Are there an oblique, or what happens? So as x goes out to -infinity, you remember what happened when we did this with the rational function? Well, we can do that same kind of thing. I've got a negative big number squared plus e raised to the negative big number, and remember how we thought of this. So this is just going to become a big number squared plus 1 over e to a big number. Well, in this case, that goes to 0. What's left is the x squared. So what we would see out to the left would be the function x squared. Now, how about what happens if we go to the right? As x goes out to positive infinity of x squared plus e to the x. Well, in that case, we're going to have a positive big number squared plus e raised to a big number, and we know exponentials beat out power functions every time. So out to the right, we would see e to the x. So it would look something like that. Okay, and then there's some stuff happening in the middle. We don't know what that is yet, and so we won't worry about that here. Okay, so now we're going to learn how to graph functions and use the derivatives to help us decide on what they look like. Some pre-calculus ideas that will help us out. I know that a function crosses the x-axis if it's a rational function with the numerator equals 0. So where does x squared equal 0? Well, that happens at 0. And if I drop in 0, I get 0 over 1, which is 0. So I know that it crosses the x-axis at the origin and crosses the y-axis at the origin, for that matter. Um, Now, are there any vertical asymptotes? Well, I know vertical asymptotes happen when there's a number divided by 0. So in this case, I want to know, where does 1 minus x squared equal 0? Well, if I extract square roots, bring the x squared over, I mean, I could factor it. Um, I think it's just as easy to do it this way for this problem. So we'll take the square root. So I got get x equals plus or minus 1. And so that tells me there's a VA at x equals -1. And there's also another VA at x equals 2. I mean, at x equals +1. And across the x-axis 0. So now here's the dilemma. Here's what I know. I know that there's a vertical asymptote here. I know there's a vertical asymptote here. And I know it crosses the x-axis here. So then I'm going to ask myself, does this function look like this and then like this? Notice I'm not crossing the x-axis out the other side of it because there's only the 1, 0. But then it could be like this, could be like this, could be like this. It could be like this. It could be like one of these, and this could be going like this. I mean, I got to come up with some decisions like that, okay? And this is where doing the calculus will help me figure that out. So now I've got to take the derivative of this function, and what I'm seeing is a quotient. So that means I've got to use the quotient rule. So the low d high minus high d low all over low squared. And then we got to clean that up, of course. So 2x minus 2x cubed plus 2x cubed. Oh, I like that. That way the x cubes cancel out. So that leaves me 2x over, this should be squared, 1 minus x squared squared. So that's my first derivative. So where's that equal to 0? Because we're looking for critical values. Well, that's equal to 0 at 0 also, and then it's undefined at x equals plus or minus 1, same as this vertical asymptote, so we knew those would be critical values because the derivative isn't defined there either. Now what we can do is we can test, you do that first derivative test, and so I've got -1, I've got 0, I've got +1. Now we're going to substitute in numbers in each of these intervals. So if I substitute in, I don't know, what do I want to substitute in? How about -10? So if that's -10 and that's -10, I'm going to get -20 over a positive number, won't I? So that's going to be a negative value. So that tells me the derivative is negative there. So then let's see. What if I drop in -1/2? That's in that next range. So -1/2 and -1/2 squared. Well, the denominator is going to be positive again. The numerator is going to be negative, -1 actually. So that's negative also. Now pick the other side of 0 and 1. Well, yeah, if these are positives, isn't it going to be positive? And same thing if I substitute in +10, it's positive. So that tells me the function's decreasing until it hits the vertical asymptote. Then it's decreasing until it hits 0. Then it turns to an increasing function, skip over the vertical asymptote, and continue to increase. So that we know. Boy, it'd be nice to move that over here so I can continue to not lose that. Let me move that right there so I don't lose everything. And then let me delete that. Oh, that's okay. And rewrite the derivative. So then now I want to find the second derivative because I don't know. Here's why. I've got that vertical asymptote here. I've got that vertical asymptote here. I've got the x-intercept here. Does this function, now it said we knew it was decreasing, so does this function, what does it look like? Does it look like this? Does it look like does it look like this? I don't know. I mean, usually it doesn't look like that. And then it's increasing, so does it look like this? I need some more work. I need some more help to do that. Because one thing I'm dealing with is concavity. I don't know if it's concave up or concave down. I'm not sure if it's, I know it's decreasing here, so it could be decreasing like that and then turning like that. So in that case, it's concave up on both sides, decreasing concave up. Well, the way we decide on concavity is we use the second derivative. So I'm going to go ahead and take the second derivative of that function, and we'll go from there. So another quotient, right? 1 minus x squared times that's the original function. Sorry, just a minute here. Let me get caught. Let me get up to speed. So let's do the derivative of the second. Let's do the derivative of the derivative. So another quotient function, another quotient. So 1 minus x squared times 2 minus the numerator times the derivative of the denominator. Well, let's see. We're going to bring down 2, leave the inside alone, subtract 1, and then do the derivative of the inside, all right? The derivative of the inside is -2x. All over the denominator squared. So that becomes 1 minus x squared to the 4th power. So now I've got a little bit of cleaning up to do here, don't I? Let's see here. So I've got to expand this, FOIL it, distribute the 2 through, and I don't have to FOIL this, but I would expand it. And I don't think you want to watch me do all that on screen. So I'm gonna do it right now off screen, and then we'll come back and talk about it. Okay, so here's a rational function, and I'm going to show you how to do this pre-calculus ways, and I'm going to show you how to. But some things we can't do with pre-calculus, because one thing, if we want to find maximum and minimum values, we need to use calculus for that. We can guesstimate with pre-calculus, but we really need to do do some calculus. So one thing I want you to notice is this is a top-heavy function, which means a top-heavy rational function because the degree of the numerator is bigger than the degree of the denominator. So this tells me there's no HA, there's an oblique asymptote. So let's find that. Let's take care of that. And this is something from pre-calc. I know it kind of, I mean, by the time we get to this in rational functions, most of my pre-calculus students are fried. We don't spend a lot of time on this, but we do talk about it. So you guys are up, being calculus. You're a little bit more with it at this point. So we'll help you through this. Okay, so I'm going to do some long division. I could do synthetic division. Often when I'm doing this technique, when I'm trying to find the oblique asymptote, I'll use long division. And all long division is just like regular division, right? In case you're a little rusty with that. So you ask yourself, the divisor goes outside, the dividend goes inside. You ask yourself, what times x gives you x squared? And of course, we just say, well, it's x. So then what we do is we multiply x times x and x times -1. And x squared minus x, and then just like with regular division, we subtract. Arithmetic, right? We subtract. Now I put together, the x squareds are gone, I'm left with x, and I'm going to bring down a 0 just as a placeholder. So then I ask myself, what times x is x? Well, that just happens to be 1. So plus 1 here. Let me write that in black, okay? I'm doing that. So x minus 1, 1 times x minus 1, x minus 1, and then we're going to change our signs, right? So I'm left with the remainder of 1. So what I'm going to get is, and you might have seen this in another video or looking at the textbook, I can write these top-heavy functions as the quotient plus the remainder divided by the denominator. And I would write these as functions because it could be a function on numerator and denominator. So in this case, our function on the numerator is 1 because it's a remainder. It's a constant function. Okay, so so right now still doing pre-calc ideas, algebra 2 ideas. So let's write this here. You know what I'm gonna do? I'm gonna delete this. And I think I wrote this once, but here I'm gonna delete all of this stuff. Give me a minute here, folks. I'm sorry. Oops, no, I want that. I don't want to delete that. There, I think that's good enough. So I'm rewriting this as x plus 1 over x minus 1. And now I hope you see it's a little bit easier to take the derivative of this. Well, do we need to take the derivative of it? Maybe not yet. Let's stay in pre-calculus mode for a minute. Now, because it's top heavy, I know there's no horizontal asymptote. There's that slant asymptote. And then there's no zeros because well, actually there's a 0. Let's go back to the original. We know 0 divided by a number is 0, so when x equals 0, it's a 0. And I also notice that it's multiplicity 2, right? So that means it's going to bounce off that. So and then there's a vertical asymptote at x equals 1, right? So far I'm just doing pre-calculus, algebra 2, whatever. So here's my vertical asymptote. Here's my 0. I know that the denominator is acts like 1 over x versus if it was like 1x minus 1 squared, it would act like 1 over x squared, which 1 over x squared acts like this, right? It would act like this, right? Versus 1 over x usually acts like this. Okay, so we know that. Let's do some cleaning up here. Do some erasing. So, whoops, not redo, undo. Whoops. All right, let's redo the 0. So now I know just from my pre-calculus work, this has to come up. Because it never, well, I know there's a vertical, let's do the oblique asymptote. Oh, I almost messed that one up. So this is a slope of 1 and a y-intercept of 1. So up 1 over 1, up 1 over 1, down 1 over 1. And this is really a dotted line because this isn't part of the graph. This is just a guiding principle. So what does this graph look like here? Let me erase this. So I know it looks something like this. It comes up, follows that horizontal asymptote, kisses that graph right there because it's going to bounce off it because it's multiplicity 2. And then it's got to turn down because it can't turn back up because it can't cross the x-axis anyplace else because there's only that 1, 0. And since there's only that 1, 0, this graph has to act like this up here. It has to come down, turn around, and head back, follow that oblique asymptote. So to me, it looks like there's a minimum here, there's a maximum here. And I know the maximum is the origin, 0, 0. I just know that because of what I know. But I don't know what that minimum is there. So this is where we need to do calculus. That's why it gives you a little bit better ideas of what to do. I want to look for concavity. I see that this function is concave down here and concave up here, and those are the mins maxes. So I'm going to have to find the first derivative, check for mins and maxes, use that first derivative test, and then I'm going to use find the second derivative. And I could use the second derivative to check for mins and maxes. I honestly never remember to do that. So let's go ahead and find some. So here's my first derivative. I did the quotient rule. I did the bottom times derivative of the top minus the top times derivative of the bottom squared. And then I distributed the 2x through, combined like terms. Then I factored out the x. So this tells me the critical values are 0, 2, because those were the derivatives equal to 0. And then, of course, it's undefined at 1 because the function is not defined at 1. And then, so I made a number line, and then I plugged in numbers into the reason I like it this format, because then it's really easy to see what I'm doing. I'm choosing the number left of 0, a negative number. I don't really care what the number is. I just know that it's negative. So if it's negative, that x is negative. If it's negatives, a negative number minus 2 more is still negative, and the denominator is always positive because I'm squaring it. And a negative times a negative is a positive, so that tells me the function is increasing when it's less than 0. So then I picked a number between 0 and 1, like 1/2. Well, if it's 1/2, that's positive. That's negative, so positive, negative over that positive denominator is negative. That tells me the function is decreasing there. Then we pick a number between 1 and 2. I chose 1/2. So 1/2 is positive. 1/2 minus 2 is still negative. Over that positive number makes it negative. And then this side greater than 2, positive, positive, positive. I didn't write that on the paper, did I? So that's positive. So that tells me the function's increasing. So the function's increasing until 0, decreasing until it hits 1, then it skips over 1, and then it's still decreasing. And then it turns around and turns increasing. Now, how about those max and mins? Do you remember from that first derivative test, which really we looked at just this week? When the derivative goes from a a positive to a negative, that tells me there's a maximum value happening at 0. And of course, we go back and plug in 0 to that, we get 0 over 0, of course, or 0, comma 0, right? Not 0 over 0. And then this one we're going to substitute, and then at 2, it's going from a decreasing function to an increasing function. That tells me there's a minimum. Notice the minimum, and that's happening at 2. So then if we replace 2 into this equation, in the original equation, that's 4 over, let's see, that is, what is that number? 2. 4 over 1, so that point there is the 0.14. I mean, sorry, 2,4. I could believe that. I could believe that's 2,4. All right, now the only other thing I got to verify is the concavity. So we're going to do that with a second derivative. The last couple things we want to look at are cusps and cusps. Really, cusps is what I want you to do. And I've talked with a couple of you about this online and in the live help. But what happens is if I have, so remember there's some places where the derivative doesn't exist. One of them is at a corner. And in any place you see an absolute value, like if I have sine of the absolute value of x, that's going to look, what's it going to look like? It probably is going to be something like this. I think I don't actually remember what happens, but this is what I'm focusing on, right? Because I know sine x usually that's where they point us. So, and I know if I zoomed in, if I graphed this in a graphing calculator and zoomed in, I would see a corner here because it's an absolute value. So it doesn't matter what the function is. If there's an absolute value in it, it's going to have a corner. The other place where that occurs is if you have the square root of x squared, because the squaring, whatever number you substitute in gets squared, and then you take the square root of it. So it's always positive. So that'll also act like an absolute value. So that's that. And then the other thing that can happen is what happens with here, just a minute here. So the next thing can happen is if I have, suppose f of, let's take a pen, f of x equals x to the 1/3. Well, what happens with that is those look something like this. And I hope you notice that this looks like a vertical line. And I know the way I know it's a vertical line is because if I take the derivative of that function, I get 1/3 x to the negative 2/3. So that gives me 1/3 times the cube root of x squared. X can't equal 0. When x equals 0, that's 1/0, which is a vertical line, undefined slope, right? So I know it's a vertical. That's a vertical tangent. The derivative doesn't exist there. So that'll happen to 1/5. Anytime the denominator's an odd number and the numerator is an odd number. Okay, now what happens when there's an even number on top and odd number on bottom? That goes, if you think about it, if an like x squared. So if I had x to the 2/3, I can rewrite that as x squared and then take the cube root of that, right? Remember, multiply powers. So that would take any negative number, turn it positive, and then take the square root. So do you see what would happen here with this piece? It would make those y values positive. So it looks like this. So that's a cusp. So that occurs when there's the top that's a rational exponent, the numerator is positive, the denominator is an odd number. Okay, not differentiable. And for this function here, it's just this one, it's just x to the 2/3 shifted right 1 unit, right? So, I mean, then you can go with the analysis. If you don't remember that, you can always do the analysis, right? I'm just trying to get you, not make it painful. If I want to do the derivative, right, wouldn't that be 2/3 x minus 1 to the negative 1/3? And then if I want to do the second derivative, that would be negative 2/9 times x minus 1 to the 4/3. Now, this I'm going to rewrite as 2/3 times the cube root of x minus 1. This one I'm going to write as negative 2/9 times the cube root of x minus 1 to the 4th. In both these situations, the derivative is not defined. First derivative is not defined at x equals 1. And there's no zeros, right? There's no zeros here. That's never equal to 0, and that's never equal to 0. So if I wanted to do some testing here, I could say, okay, here's f prime of x. It's happening. The only critical value is at 1. If I substitute in 0 in, say, where's my derivative here? If I substitute 0 in, isn't that negative? Because it'll be the cube root of negative 1, and 3 times the cube root of negative 1, so it'll be 2/-3, which is negative. And then go to the right of 1, and then it'll be positive. So that tells me the function's decreasing. Remember, this is going to decrease at negative 1, so it's going to be decreasing until there, and then it's increasing after that. See how that's working? And then how about concavity? Well, what's happening with this one here, let's see See how that's to the fourth power? So it doesn't matter what number we substitute in, it's always going to be a positive number, right? Because we're raising to the fourth power, taking the cube root, still a positive number, and the numerator is negative. That tells me the second derivative is always negative. So concave down. See how that's always concave down? So you can get there doing the calculus. It's just that remember these shortcuts. It makes it a little less painful. Okay. Just a minute. Okay, so for this question, I decided to tackle this with algebra, not using any calculus yet. And I factored the numerator, factored the denominator. Where the numerator is equal to 0, then I know that's where it crosses the x-axis. So x-intercepts are at -2 and at +1. Is where the denominator is equal to 0 is where the vertical asymptotes happen. Same power, so horizontal asymptote is y equals 1. And let's see, then the y-intercept, I substituted in 0, 0, 0, 0. That can mean -2 over -4, which is +1/2. And I guess that's all I can get out of it without doing any calculus. So then I'm thinking about this is, how the heck can this happen? Well, I know this can't cross the x-axis. It's got that horizontal asymptote. So I know it's got to go down like this. And then it can't come back up, so that's stuck. And then this part, it's got to come down. It's got to come down like this. And then this has to be like that. And it has to be above the line because it can't come down below that. So that's a pretty good estimate of what it looks like. Now, what am I missing? Are there any minimums? I don't know. Are there any local maximums? Maybe, maybe. I don't think so. The other thing I don't have is my concavities. I think this is concave down here. I think this is concave up here. I think this might have a point of inflection there. I don't know. I really would need to do the second derivative to check that out. Okay, but let's just check out the first derivative and make sure it's interesting. So what I should be getting, looking at my graph, that the derivative is always going to be negative, looking at this. So it's a quotient. I had to do the quotient rule, low d high minus high d low over low squared. Here I tried doing something with factoring out, and of course, as you can see, that didn't get me anywhere. So I said there's no common factors. I couldn't do any factoring by grouping. So I'm kind of to do much more, I'm going to need to expand all of this out. So that's what I did, as you can see. I foiled that. Let's see, what did I do? Maybe I didn't write it down here. What did I do? Yeah, I didn't write down the first one. I did write down the second one. So what I was doing here, let's see, I was expanding. Where's my graph? Where's my other function? So what I was doing here is I was expanding x squared minus 3x minus 4 times 2x plus 1. So that's why I went 2x times x squared and 2x cubed and so on and so forth. And I did the other one. So this was the low d high minus high d low over low squared, and then of course I did some canceling out, and that's what I ended up there. And I noticed I could factor out a -2. So now where I want to go is I want to see well, I know it's not. I know that there's a vertical asymptote. This factors to x minus 4 times x plus 1. So I know there's going to be VA at x equals there's a critical value because these are the vertical asymptotes, right, at 4 and at x equals -1, just like we did with the original graph. But the numerator was interesting. Let's see I want to find out where is that equal to 0. And of course, the factors of 5 that will add to give me 2, I don't think that's going to happen. So let's see, I applied some more algebra to this next slide. Okay, so on this next slide, what I did here is I said, I want to set that equal to 0. So I got this feeling that it might not be factorable. In fact, I'm pretty sure it's not factorable. So what I did is I used the discriminant, remember b squared minus 4ac, and if this is not a perfect square, it's not factorable, And what happened here, it's negative, right? 4, negative 2 squared is 4, minus 4 times 1 times 5. Well, that's a negative number. That means there's no real zeros. So that means the derivative is never equal to 0. So the only critical values are at the vertical asymptotes. And so I guess I could plug those in and see. Let's see. So at -1 and at +4, is it? And then I've got my derivative, which is, where's my derivative? Here. Come on, board. Stop flipping. I'm just going to get that out of the way because I don't need that anymore. -2 times x squared plus 2x plus 5 all over x squared minus 3x minus 4 squared. So the denominator is always squared. So that's always going to be a positive. So if I pull a number in, like if I pull a number in over here, like negative, I don't know, -100, that would be +100 minus 20. Negative. What if you do -10? That way it's, so that's 100 minus 20 plus 5. Well, that's going to be a positive number times a negative number makes it negative. Negative divided by a positive is negative. Now let's pick a number like 0. Well, if it's 0, it's going to be +5 times -2, which makes it negative, and the denominator is always negative. And then pick a number bigger than 4, like 100 or 10. Again, positive times that -2 over the positive makes it negative. So this tells me, remember, this is f prime of x. This is telling me the function is always decreasing, except onto those vertical asymptotes. And that agrees with what I had in the graph, if you remember how that looked. Okay, now the concavity issue requires second derivative. Pain in the butt, I think, to get the second derivative. Okay, as I said, the second derivative would be a royal pain to calculate by hand, so I'm showing you I like Wolfram Alpha. I also like Symbolab. For some reason, Symbolab wasn't working for me this morning, so I used Wolfram Alpha, and it gave me the derivative. Would I expect you to be able to do that by hand? Well, I mean, you should be able to, but to clean it up would be a pain in the butt. So I'm going to give you other fish to fry rather than cranking through all that algebra. But here's the second derivative. And then what I'm really curious about for that concavity question is look for critical values on there. Well, I know there's a critical value at +4, because that's the vertical asymptote, right? And same thing with -1. But then I'm wondering, where does this equal 0? So I went ahead and graphed the whole second derivative in Desmos, and I'll let you go verify this. This never rises above the x-axis here, and this never goes below the x-axis here. It does go by the x-axis right there. So because the second derivative is positive, that means the function is concave up between -1 and 0.787. And that it's concave down between 7.7 and positive, or at +4, right? So if you go back and take a look at that graph, right, you can see where see how it's concave down. Let's see, where am I? I want a pointer. All right, concave down. And then it's concave up, and then it kind of somewhere in here. I couldn't find that, but that's where there's a point of inflection there. It must be at 0.7, and that's pretty close to 1, I believe that crosses. So see how that did work. I mean, just using the pre-calculus technique, we did okay. And there's no, of course, there was no minimums and maximums, right? Because it was never equal to 0. The first derivative is never equal to 0, right? Right, it was never equal to 0, so it was always decreasing. And then of course it's not defined in the vertical asymptote. So there's no local min maxes either. No absolute either, but no locals. Okay, so there's that.